Hello, my name is Allison Bushman, and I am a member of the Robotics Automation and Dance Lab directed by Dr. Amy LaViers. Today I will be presenting our paper titled Toward Human-like Teleoperated Robot Motion, Performance and Perception of a Choreography-inspired Method for Rapid Post-Selection of Articulated Robots. The global pandemic with which we are currently faced has underlined the significance of telepresence. As shelter-in-place orders and travel bans are extended, people have come to recognize the social benefits of telepresence in human-facing environments, such as social gatherings, the workplace, shopping, and even travel. Furthermore, the new world catalyzed by COVID-19 will see further integration of artificial bodies into dangerous environments within the fields of medicine, space exploration, first response missions, and even police work. However, teleoperated robots are faced with a cold and rigid connotation. While automating voices to sound sweet and helpful may attenuate any concerns human collaborators have, verbal communication is but one medium that humans use. Our work seeks to understand how to generate more fluid and human-like motion for an articulated robot such as the Rethink Robotics Baxter robot. Here, we present a choreography-inspired method of teleoperation control named Robot Choreography Center and test it against a traditional joint angle by joint angle method of control modeled after the controls used by the military in controlling the PackBot. Previous work has developed the teleoperation scheme and tested it for a single researcher using 4 tasks, which were categorized as either one arm or two arm, as well as static or dynamic. This created a range of difficulty for which the 2 methods of control could be tested. In this work, static tasks were defined as tasks that required a specific end configuration, such as placing 1 or 2 arms through hula hoops, as seen in Task 1 and Task 2 in the leftmost video. Meanwhile, dynamic tasks required an exchange of momentum. Task 3 required the operator to control the arm of the robot such that it was able to hit a balloon into a whiteboard, as seen in the middle video. And Task 4 increased the difficulty further by adding an obstacle between the robot and the balloon. A 2-hour in-lab user study was conducted with 38 participants from the University of Illinois, none of whom were familiar with the choreographic concepts utilized in this work. For both the joint-by-joint and choreography-inspired methods of control, participants engaged in a movement training prior to teleoperating the robot. This was done to help them understand how the concepts of each teleoperation method related to their own body. The figures provided on the left and right were used as references for the teleoperators to understand how the joint-by-joint and choreography-inspired methods of control were mapped onto the Xbox One controller and the Baxter robot. For the joint-by-joint method, the movement training involved placing a hand on a shoulder or a hip by moving only a single joint at a time. As shown on the left, the controls are slightly simpler since the teleoperator is only controlling one joint at a time. Meanwhile, the movement training for the choreography-inspired method of control taught participants 2 key concepts, kinesphere and spatial pull. Kinesphere, as denoted by the small pink circle in the bottom right, is the volume of space through which a body part is able to move. Participants were taught 3 kinesphere sizes that the robot was capable of achieving: near reach, middle reach, and far reach. Next, they were taught about spatial pulls, which require both plane and direction. As shown, there are 3 planes, high, middle, and low, as well as 8 directions, forward, backward, right, left, and the diagonals in between. These concepts required a slightly more complex command system, shown by the addition of the face buttons and directional pad to control the kinesphere size and plane, respectively. After learning all of the necessary concepts and practicing them on their own bodies, participants had to take a short verbal test showing that they understood the material before moving on to actually teleoperating the robot. The resulting motion for each method of control is shown on the next slide. These videos show the Baxter robot being commanded to put one arm through a hula hoop, with the left and right videos corresponding to the joint-by-joint and choreography-inspired methods, respectively. For the joint-by-joint method, notice that individual joints are controlled in a sequential fashion, with each joint capable of extension and flexion as well as rotation. This leads to an average of 1 joint moving at any given time. Meanwhile, for the choreography-inspired method, we see that multiple joints are moving simultaneously. Previous work has determined that an average of 3 joints may move at any given time. This led us to the hypothesis that the number of joints moving would affect not only performance metrics associated with completing a task, but also the perceptions of the operator using the 2 methods of control. Compensation was based on the ability of the participants to successfully complete the 4 tasks using both methods of control. Therefore, we can look to the bell curve shown in the upper left figure to determine the relative success of the participants. The column shown at 55 indicates that the most number of participants were able to complete Task 1 and Task 2 for both methods of control, as well as reach the waypoint for Task 4, which was moving the obstacle out from between the robot and the balloon. However, surprisingly few participants were able to perform better than this, with only 1 participant being able to complete all 4 tasks for both methods of control. The performance metrics for each task were then analyzed, and the results are shown in the bottom right figure. As shown by the red columns, both methods of teleoperation were over 80% successful for static tasks such as Task 1 and Task 2, with a sharp decrease in success rate for dynamic tasks. While the amount by which the success rate dropped was somewhat surprising, we had expected a decrease due to the increased difficulty of the dynamic tasks. However, the lack of success for dynamic tasks indicated that we needed to increase the training time for Task 3 and Task 4, such that participants had more time to grow accustomed to the control scheme and develop a successful strategy to achieve these tasks. That being said, the choreography-inspired method was an average of 11.85% more successful for the dynamic tasks. In addition to success rate, we also looked at the time it took for successful participants to complete each task. The average task duration is shown in the blue columns in conjunction with the secondary y-axis. Both methods of control had relatively similar task completion times for Task 1, but the traditional joint-by-joint method of control proved quicker for Task 2. Additionally, the joint-by-joint method of control appears to be quicker for Task 3, but it should be noted that the success rate for Task 3 using the joint-by-joint method is lower than that of the choreography-inspired method. Therefore, the average task duration shown is only that of the top 2 performers. Meanwhile, the choreography-inspired method of control yielded greater success, increasing the data pool to calculate the average task duration. Finally, Task 4 indicated that the choreography-inspired method of control was both quicker and more successful than the traditional joint-by-joint method of control. We further analyzed the 2 methods of control using the perceptions and preferences of operators. The statistical significance of these results was determined using a 95% confidence interval. Any of the columns whose value exists outside of the confidence interval is considered statistically significant. First, the overall findings in green suggest that the traditional joint-by-joint method was deemed to be more precise, easier to use, safer, and more articulate, while the choreography-inspired method of control was considered faster, more fluid, and more expressive. Interestingly, the results indicated that the preferences of users was dependent on their performance during the study. In looking at questions 9 through 13, we see that the lowest performance bracket preferred the joint angle by joint angle method of control, while top performers preferred the choreography-inspired method for dynamic tasks such as Task 3 and Task 4, as well as any potential future tasks that they may encounter. Ongoing work has found that secondary observers choose similar labels to describe the movement profiles of the 2 methods of control. In addition to finding the choreography-inspired method more fluid and more expressive, the responses of a new pool of participants indicate that observers also find the choreography-inspired method to be softer, more graceful, more natural, and more human-like. Meanwhile, the traditional joint-by-joint method of control is seen as more precise. These results further support the hypothesis that the choreography-inspired method of control produces more fluid, natural, and human-like motion. Human expression is an inherent part of our existence. Therefore, robots placed in human-facing scenarios must also have this capability in order to adequately function in dynamic environments. Thank you very much for listening.